Welcome back to Fat Mama Physics. This is a new set of videos I'm making for the gravitational fields topic D1HL for IB Physics. In these series of videos, I will do a combination of lecture and tutorial videos, and also I've brought two little mascots that I'm going to use for some of the examples to show. Of course, if I did this in class, I'd be making more fun of you guys instead of these guys. But a little bit of background. This guy, his name is Shin. If he is the stuffy of the actual singer Zhou Shin or Charlie Shin. Charlie Zhou, who is our household celebrity favorite for a singer, and he is also one of his songs I parodied is called The History or Fu Guang in one of the shorts. So he's a household favorite. So he is Shin. Then you got Lulu Pig. So these are two mascots I will be using. And then Lulu Pig, of course, we love Shin. He is amazing singer, beautiful voice. All right, so this first video on gravitational potential energy, I've broken down into two videos. The first one is to kind of give you an idea of what the gravitational potential energy is, the definition of it, what are the components, the variables or things that go along with it. The second video is when I will actually talk about the implications or what does everything mean, okay? So they come together as two. So, putting these guys aside, gravitational potential energy. We've always been used to gravitational potential energy being mass times gravity or gravitational field at the surface of the Earth times height. Now, based off of what I said, you probably noticed there is a problem in which this calculating gravitational potential energy here is very restrictive to just the surface of the Earth. Because as you go higher and higher above the surface of the Earth, the gravitational field gets weaker. So this constant here, G, is not going to be 9.8 forever. So there are many cases where we can't use this. You also might recall that in when we learned about circular motion, we talked about Newton's universal law of gravitation and the gravitational field being big G, so gravitational constant, times the mass of your point mass, your big object, divided by the distance of separation of that object to your position in space relative to the center of mass of your point mass. So gravitational field, of course, is variable depending on how further away you are by an inverse square law relationship. And it also defines that, it also has a definition in which your reference point is on the ground. When H is 0, meaning at the surface, we define that as zero potential energy. Now, why are we so special? Why is the surface of the Earth so special in relation to the rest of the universe? So that is going to have to undergo a definition change as we talk about gravitational potential energy. So what is gravitational potential energy, or what is this new definition? I might jump around a little bit, but the definition is here. Gravitational potential energy is the work needed to bring two masses, got you two masses, from infinity, I think they're off screen now, okay, to a set distance between them. So imagine I have to push them together, let's say 10 centimeters apart. This is relative to where I am, maybe not so much on your screen, okay? So imagine this is 10 centimeters apart. The amount of work I did to push them from infinity to this point is your gravitational potential energy, is the work done. And because I said work done, this automatically applies that the units of this is in joules. Now, there's also something interesting about this definition is a new reference point. And this is something that we're going to talk about more in detail later, but the fact that these two lovely creatures start off at infinity. Okay, so that's something to pay attention there too. The next step is to now quantify this amount of work. in relation to your two objects' mass. And of course, what does it mean from infinity to a set distance apart? And with that being said, we want to go to a core definition of what is work. Okay, so work, based off of what we learned in classical mechanics, is force times displacement. That means under a force versus technically displacement time graph, okay, imagine you have force on the y-axis and you have some sort of distance, or you have a distance measurement in your x-axis. That means force times displacement is your work. On the graph, and this is where you can do a quick review, it's either slope or area. Take a quick second to guess which one it is. And yeah, you're right, it is the area. It is the area underneath a force distance graph, and that should give you the work done. The reason why I want to start with this definition of work is because we can find the amount of gravitational force of attraction between two objects. So if I place Shinshin and Lula Pig 10 centimeters apart, they are going to feel force due to attraction between the two that is in direct proportion to their mass and inversely proportional to their distance of separation from their center of masses squared. That is Newton's universal law of gravitation, in which Fg is the Newton's gravitational constant times mass of object 1 times mass of object 2 divided by your distance of separation from their center of masses squared. And here I have this sphere actually here. So the graph of this would show an inverse square relationship, so this would look like this. You might be wondering what this sphere here is for, though this sphere is, originally my example was in relation to the surface of the Earth, or to Earth itself, in which here you have Earth's radius. And then as you go further along, then this R value then increases for their distance of separation. And the area underneath this graph would be then this, that I'm shading in. And of course, area is always underneath the graph up to the x-axis. So the next question is, how do we then quantify this area? Well, if you have a little bit of calculus background, you can probably take the integral and figure it out. I don't expect you to, and nor the course expects you to do that, but I think it's really fun and cool to see how math and physics interplay with each other. And also, if you do study calculus, it'll be really cool that while you take calculus, go back to this concept when you are learning integration to solidify your understanding in both calculus and physics. For our purposes, I'm still going to go through it. Of course, I'm not going to do as good of a job as your calculus teacher will do it, but of course I will bring in the physical or the physics so that it will help you, I don't know, later when you study calculus. So I will go over this. If you haven't studied calculus or this is not going to make sense to you, please feel free to skip the video. I think this will roughly be about, I don't know, 2-3 minutes. And of course, if there's a timestamp, you can use that as well. In this part of the video, I assume that you know some basic calculus in terms of integration, and also the antiderivative of course, certain functions, such as your Newton's universal law of gravitation. So here I have the work done, which is by definition, gravitational potential energy is the work done needed to bring two masses from infinity to a set distance apart. And we're going to integrate this from a lower bound of infinity, so that's where they start off, up to R, which is the distance of separation between those two. So those are going to be our boundaries, okay? The equation that I have here, this is Newton's universal law of gravitation, because this is the graph in which we want to find the area underneath. This dr is to cut up all the graph into these small pieces, and then of course summing it all up and adding them all together. So the first step here is to find the antiderivative of big G, big M, small m over r squared. Do keep in mind that big G, big M, small m, sorry, the two m's represent two separate masses. So in our context here, you can have, Shinshin and Lulu Pig. I like to think of Shinshin as the big M, Lulu Pig as the small m. The key here is that these two m's are constants, including the gravitational constant itself. So in a way, what we can do, we can put them outside of the this little thing here called the integral. So really, I'm breaking it down even more this time. Okay, so it would look like this because they are constants, and therefore we are now left with this 1 over r squared. To find the antiderivative of 1 over r squared, and this is something you get better at with continual practice, you tend to then start to memorize these things. It is negative 1 over r. And of course, the boundaries are still going to be from integrating from infinity to distance r apart. We do big G, big M, small m, and then our final is going to be r. Essentially what we're doing is we're substituting this r value for the r and then the infinity. So you're right, there's still going to be a negative sign here, and I'm squeezing in right there. And then minus lower bound, and this is going to be, there's also going to be a negative sign coming from this negative 1 over r, minus big G, big M, small m, and on the bottom, this is an infinity sign in which it's not really proper for me to put that, but essentially what that means is as r approaches infinity. I'm going to put up infinity sign just so it makes it easier for me to kind of interpret that, because what happens now is if this r value here on the bottom approaches infinity, that means the whole term approaches 0. So I'm going to go like this, draw an arrow like this, that approaches 0, in which the second term then becomes, we lose that second term, and we get, as a result, negative big G, big M, small m over r. Big R, all right, big R. And that is going to be our work done to bring two masses from infinity to point r of separation. If you don't believe that this is the integral, or this is the area underneath the graph, what you can do is you can then take the derivative of this and see if you get Newton's universal law of gravitation. So if I take the derivative, imagine this is r to the power of -1, right? So whenever you take the derivative is you drop the exponent to the front, and then you then decrease the exponent by another one again. So, okay, so I wrote it like this just to make it easier. So here this -1 drops down in front. So you get negative of a negative, big G, big M, small m, and then this r's exponent drops by another one, which becomes -2. A negative and a negative makes a positive, and then this r to the -2 then becomes an inverse square law relationship, which is your Newton's universal law of gravitation. So everything works out perfectly. And if you do check your data booklet or your formula data booklet, indeed, gravitational potential energy is negative. There's a negative sign, big G, which is your gravitational constant, times the mass of object 1, big M, mass of object 2, small m, over r, which is your distance of separation from those masses, center of masses. So I'm just going to write out all of those constants, or what those symbols mean. Gravitational constant, which is, we all love this number, 6.67 times 10 to the power of -11. Units, newtons times meters squared over kg squared. And I know I should have used the exponents just running out of space there. M is your mass of your bigger, typically your bigger point mass. Just going to put here bigger and bigger mass measured in kilograms. Oh my goodness, running out of space. In the context of our little storyline, that's going to be our Shenshen because he's just that attractive. Okay, so much mass, right? More mass, more attraction. Okay, then you have small m, which is the mass of your, let's call it a test mass or like a smaller mass, also measured in kilograms. And I apologize for the small writing. Annotated notes on Teams so you can check marginally better writing. I guess in hindsight should have typed it out instead. And then in our storyline, that's going to be our Lulu pig, the smaller mass, even though pigs tend to be very massive. Anyway. And R is I used a big R, so let me just change that to a small, it's not the same. Right, fine. I'll keep it as R and I'll make this big R here. Okay, so that's the distance of separation from big M and small m's center of masses in meters. I gave up writing it because my writing is just so bad. So kind of going back to this definition of gravitational potential energy and it being work done in bringing two masses together, you may also have noticed something interesting, which is, I'm going to erase this later because it's not really official. I don't really like it. But if you go back to the idea that work, don't write this down, work is force times distance or displacement, then in the case of Newton's universal law of gravitation, this is going to be big G, big M, small m over r squared. Now, if you multiply that force by a distance, dimension, or anything that has to do with meters, which in our case could be r, for example, then you might notice that, hey, one of the r's cancel, and you just so happen to get big G, big M, small m over 1r. And you might, hey, that's kind of like a cool shortcut in a way. There's a very good reason why it is a shortcut. It is not proper to go with that definition. And of course, one of the key things, well, not just one of the key things. First, you'll notice that there is no negative sign. That negative sign is very important, which I'll talk about in the next video. But the other thing that we also need to appreciate is that the force of attraction between your two masses is not constant as you move them further or closer together. And because it's not constant, this equation here breaks down because this assumes that this force is either constant or is some sort of average, which would be very difficult to do in this case, which is why the integration, the calculus way of finding it is more proper. But at our stage, we don't need to understand or to be able to derive it using calculus, but it would be a cool thing and something I would like HL students to be able to appreciate eventually. So the key things I want to highlight in this video is we now have a new definition of gravitational potential energy, and it is the work needed to bring two masses from infinity to a certain distance apart from their center of masses. We now redefine where that reference point is. It is no longer the surface of the Earth. We are not special. And in fact, it has something to do with infinity, which we will talk about the significance in the next video. Also in the next video, I will feature what this negative sign means and why there is a negative sign when calculating for the gravitational potential energy. Otherwise, thank you for bearing through my antics and the cheesy storyline. I hope you got something out of this video, and I will see you back in part 2 of gravitational potential energy. Fat Mama Physics, signing out.